Hello everyone, my name is Tanuja Khan, Assistant Professor, Department of Education, BSSS College. Today we are going to discuss analysis of variance, two-way classification. In the previous video, we have covered analysis of variance for one-way classification, introduction of analysis of variance, then assumption and classification of ANOVA one-way classification, and working rule of one-way classification. We also covered the problem based on one-way classification of ANOVA. In sequence, we are going to cover analysis of variance in two-way classification. Now, what is two-way classification and what is the difference between ANOVA one-way classification and ANOVA two-way classification? In the previous video, we discussed about one-way classification, that one factor is involved in one-way classification. We also solved one problem based on varieties of rise, in which we have taken one factor, that is variety of rise. Now, if the factor will increase, like with the rise variety, if the plots are different, then two factors involved in that problem. So that problems will reflect the two-way classification of ANOVA. The definition for the two-way classification of ANOVA is the representation of data in the form of influence of two factor or cause. We already discussed about the assumptions of the ANOVA, and that assumption is followed here also. Now the working rule for ANOVA two-way classification. The working rules are setting up of hypothesis. Second is the correction factor. The third one is to find out the SST, that is total sum of a square. The fourth one is the sum of a square between the columns. The fifth one is the sum of a square between the rows. And the sixth one is the sum of a squares between the errors. The final and the most important steps or the working rule of ANOVA two-way classification is to draw a ANOVA table. And the last one is to find out the conclusion or draw a interpretation from the data. Let us take a problem and understand how ANOVA two-way classification will be solved. Now the problem is, the following data represent the number of units of a product produced by three different workers using three different types of machine. Now here two factors are, one is machine and another one is worker. Now we have data for machines and workers. Now what we have to find out from these data, first one is whether the mean productivity is the same for the different machine types when the table value of F for DOF 2 and 4 at 5% level of significance is 6.95. And the second is whether the three workers differ with respect to the mean productivity when the table value of F for degree of freedom 2 and 4 at 5% level of significance is 6.95. Now solution. As our working rule, the first working rule is setting up the hypothesis, and in this question we are going to form a null hypothesis, and our null hypothesis are, the first one is the mean productivity is same for the three different machines, and the second hypothesis is the workers do not differ with respect to the mean productivity. Now the second working rule for ANOVA two-way classification is the computation of test statistics, and for the same problem we have to total horizontal values, that is for the workers, and we have to total the vertical values, that is for the machines. After that we have to find out the mean for the machines. Now after this total, we have to find out the correction factor, and formula for the correction factor is C is equal to T square divided by N. This is T square divided by N. Now RT, as per the previous slide, RT is the grand total of all the items, and our total is, RT is 210. N is the total number of items, which is 9. So correction factor, that is T square divided by N, is now 210 square divided by 9. So 210 square, that means 44100 divided by 9. So our correction factor is 4900, that is 4900. Moving forward for the next working rule, that is to find out the sum of a square. Now formula for SST is sum total of x square minus c. Now in the table given here, we have all the values. We have 8, 28, 6, 32, 36, 28, 20, 38 and 14. Now for SST, we have to square each and individual values and subtract from correction factor. Now moving forward for the next working rule, that is sum of a square. To find out the sum of a square, that is denoted by SST. Now SST is nothing, it is the difference between all the individual squared values and correction factors. Now for this step, we have to square all the individual values and correction factor subtraction. After getting the values of all the squares, we have 64 plus 784 plus 36 plus 1024 plus 784 plus 400 plus 1444 and 196. The sum of all the values is 6028 and the subtraction between the 6028 and 4900 is 1128. Now our SST is 1128. After SST, we have to find out SSC, that is the sum of a square between the columns. Now for SSC, that is denoted for machines, we have to square the total of the columns. The machine totals, the vertical total of the columns, which is 42, 36 and 72. We have to square all these values and divide it by the number of item in that particular columns. Now 1 by 3 is common in all, so we are taking 1 by 3 as common. Square of 42 is 1764, square of 96 is 9216 and square of 72 is 5184. Now SSC, as per the formula, it is the subtraction between all these values and correction factors. So we have value 5688 minus 4900, that is 488. So our SSC is 488. Moving forward for find out the SSR. Now to find out the SSR, that is sum of square between the rows, we followed all the steps which we already conducted for SSC. Now the formula for SSR is square of all the row values divided by the number of items in that particular row minus C. C is your correction factor. So here SSR is 60 square divided by 3 and then 102 square divided by 3 and 48 square divided by 3 minus correction factor, where 3 is the number of item in each row. Now we get 1 by 3 in bracket 3600 plus 10,404 and 2304 minus correction factor, and our correction factor value is 4,900. For the next step, we have 5,436 minus 4,900 and that is 536. Now the last sum of a square, that is sum of a square for error. It is also known as the residual part of the data, and formula for SSE is SST minus SSC plus SSR. Now we have all the values. We have SST is 1128 minus we have SSC 488 and we have SSR, that is 536. So after calculating all these, we have 104, that is our SSE. Now ANOVA table, this is the most important part of ANOVA solution. Based on this table, we will be able to interpret the data as per our hypothesis. Now for ANOVA table, we have all the values. We have SSC, we have SSR, and we have SSC. Now this is new, this degree of freedom is new for you. So how you are going to calculate this degree of freedom? Like in ANOVA one way, same procedure is followed in ANOVA two-way analysis also to find out the degree of freedom. Now the first, for the machines, we have three categories in machines. So total number of machines categories -1, that is 3 minus 1. So degree of freedom for machine is 2. Same for the workers, we have three categories of workers. So the degree of freedom formula for the degree of freedom is n-1. So 3 minus 1 is again 2. Now for the error, we have to multiply this degree of freedoms between the machine and workers. So we have 4 for error. Now for mean squares, the formula for the mean square is sum of a square divided by degree of freedom. Now for machines, we have sum of a square between the column, that is 488, and we have degree of freedom for machine is 2. So after dividing 488 by 2, we get 244. And this 244 is mean square between the column or machines. Now for the workers, mean score of workers, we have to divide SSR by degree of freedom. Our SSR is 536 divided by 2, and it becomes 268, and this mean square is for the row, that is for the worker. And for the mean square of error, we have SSE divided by degree of freedom, that is 104 divided by 4, and it is 26. So our MSE is 26. Now the last part of the table, that is F value. This is our calculated value of analysis of variance, and the formula for F is MSC divided by MSE. Now the first F ratio, that is for the machines, FC. We have MSC, that is 244, and MSE is 26. So we have to divide 244 by 26, and it will become 9.38. Now for second formula for F for the workers, that is denoted by rho, is equal to MSR divided by MSE. Now MSR is 268 and MSE is 26 again. So our FR is 10.31. Now the most important part of analysis of variance for two-way classification is to test our null hypothesis, which we already formulated in the beginning of the question. Now for first hypothesis, our calculated value, that is FC, is 9.38, and the table value given in the question is 6.98 for degree of freedom 2 and 4 at 5% level of significance. Now our calculated value is greater than table value. It reflects like our calculated value is greater than table value. So from the rule, it is already proved that if the calculated value is greater than the table value, the null hypothesis is rejected. So in this case, as we have greater calculated value than the table value of degree of freedom 2 and 4 at 5% level of significance is greater, so our null hypothesis is also rejected. Hence, the mean productivity is not same for the three different machines. Now for the second null hypothesis, we have calculated value 10.31 and the table value is 6.95. So as our calculated value again is greater than the table value, that is 6.95. So null hypothesis in this case is also rejected. Hence, three workers differ with regards to the mean productivity.